In this video, we're going to compare the precisions of three data sets. We've got data set A here, data set B here, and data set C. And we want to see if any of them has a precision that's significantly different from the others. We have already calculated the size of the data sets just by counting and the standard deviation of each data set and the variance of each data set. The variance is just the standard deviation squared. We're going to need the variances to do this comparison. So our question is, are the precisions of the three data sets significantly different? We have to be clear on what our null hypothesis is here. Our null hypothesis is going to be any differences in the variances come purely from random error and nothing else, that we don't have some outside factor that is making the variances different. So we want to see if we can reject this null hypothesis. Now there's two ways that we can do this, we can approach this. One is to calculate an F statistic, which compares the variances for each pair of data sets, and compare that F statistic with a critical value at 95% confidence. And if our F is bigger than the critical F, that means that we can be 95% confident that we can reject the null hypothesis. So that's one way to do it. There is a much simpler way. You can calculate the p-value for the F right here. What does that mean? A p-value is the probability that you will be wrong if you reject the null hypothesis. So if we see that the p-value is 0.05 or lower, that means we have a significant result. That means that we are seeing that the precisions of those two sets are different. If we have a p-value that's 0.01 or less, that's a highly significant result, and that means we can be 99% confident that we're right in rejecting that null hypothesis. All right, so let's calculate the F statistics for each pair of data sets. And the F statistic is calculated as the ratio of the variances of the two sets. So I need the ratio of the variance in set A versus the variance in set B. But I've got to always put the higher variance on top of that fraction. So I'm going to say equals, and I'm going to come over here and see which set has a bigger variance. It looks like B does. And I'm going to divide that by the variance of A, and that gives me my F statistic for that. Now I can't just drag that cell over because I have to make that decision manually each time. I'm going to say for B versus C, if I look at the variances, it looks like B again is the bigger variance. So I'm going to put B on top. And there's my F statistic there. Now let's do A versus C. If I look at the variances here, A has the bigger variance of the two, so I'm going to put variance A on top. So those are my three F values. Now let's get the critical F values. For this, I can use the Excel function F inverse. And I'm going to put the probability that I'm going to be wrong if I reject the null hypothesis there. So if I want to be 95% confident, the probability I'm going to be wrong is going to be 5% or 0.05. Now I have to be careful here. It wants next what the degrees of freedom for the two sets I'm comparing are. And I want to put the set with the larger variance first. So when I look at A versus B, we said that the larger variance is set B. So I'm going to put degrees of freedom for set B next. There's n minus 1. That's degrees of freedom for set B. Now I'm going to do degrees of freedom for set A. There's my critical F value. Now notice that my F is not bigger than the critical F, so I cannot reject the null hypothesis with 95% confidence. Let's do the next comparison, B versus C. I'm going to use the F inverse function again. The probability I'm going to want is 0.05. And I've got to put the degrees of freedom for the bigger set next. If I'm doing B versus C, the bigger variance is set B. So I'm going to say degrees of freedom for that set is n minus 1. Degrees of freedom for the other set I'm comparing is 5 minus 1. And once again, I see my F value is not larger than the critical F value. So I cannot reject the null hypothesis with 95% confidence. Now, let's do this one. A versus C. F inverse, the probability is 0.05. The larger variance is for set A. So that means I'm going to put degrees of freedom for set A next. Oops. And then I'm going to put degrees of freedom for set B, or for set C, sorry. And again, my F value is not bigger than the critical F value, so I cannot reject the null hypothesis. Now there's a more direct way to do this, and that is to calculate the p-value. Now remember what the p-value is. The p-value is the probability that you'll be wrong if you reject the null hypothesis. So we would like this p-value to be 0.05 or less. So let's see if we get results that are consistent with the decisions that we made here. We said we could not reject the null hypothesis. Now, the function here is f-test. And it only takes two arguments. One is the first data set you're comparing. And it doesn't matter if you select over blank cells, it will ignore those. And the second one is the second set that you're comparing. Now, I got 0.87452 as my p-value. And what that means is that if I reject the null hypothesis, there's an 87% chance I'm going to be wrong. So that's a pretty high percentage I'm going to be wrong. So I should not reject the null hypothesis. I cannot really say that any differences in the variances come from something other than random error in this case. So let's get the p-values for the other comparisons. Here I'm comparing set B and set C. And I could just select the data itself, but I'm keeping the selection areas the same size every time. There's an 81% chance that I'll be wrong if I reject the null hypothesis. That's a pretty high percentage, so I shouldn't do that. If your p-value is bigger than 0.05, you can't reject the null hypothesis with confidence. And finally, the p-value for the last comparison looks like that. There's a 92% chance that I'm going to be incorrect if I reject the null hypothesis. So I shouldn't do it.